Buenos días. The lecture today is called Simultaneous Uniformization by Kleinian Groups. I will explain later the meaning. And I will use abbreviation like this. And like this. It will be Kleinian groups or Kleinian group according to the context. So a goal is similar to what I have plotted yesterday. We have a family of algebraic curves but now one of them is not topologically equivalent to the others, to the nearby one. It is a critical level with a Morse critical point. Something like this. And the topology of the leaf remains the same for all the points of a cross-section except for one. And one point on the cross-section corresponds to a leaf with a different topology. So this is what I want to present you today. But first of all, we go back to quasi-conformal mappings. Once again, I will use the abbreviation like this. First of all, let us consider a very elementary topic, a linear functional, complex linear functional on the complex line. We have three cases when the ratio of the magnitude of these two coefficients when the ratio of the magnitudes of these two coefficients is smaller than 1, then orientation is preserved. When it is greater than 1, then the orientation is reversed. And when it is equal to 1, we have a degeneracy. The image is a real line rather than the whole complex line. So this is a very elementary preparatory material. Now consider a complex map of a domain omega to C. The differential of f again equals to a dz plus b dz bar. A is called the derivative of f by z. B is the derivative of f by z bar. Their ratio is the Beltrami coefficient. The Beltrami coefficient. A quasi-conformal map if it is C1 smooth and has a continuous differential, then f is quasi-conformal provided that magnitude of mu is smaller than q smaller than 1 in the whole of omega. And that's it. Geometrically, this means the following. df is a complex linear map at any point. It maps a circle to an ellipse. And the eccentricity of the ellipse, the ratio of its large and small axes, is bounded in omega. Let us give another geometric illustration of quasi-conformal mappings. Let us plot here the maps here. We will write whether a conformal map of this kind does exist. Plus exists, minus no. First, we consider a map of an annulus This is a circle of radius r. This is a circle of radius 1. And we want to map it onto an annulus. We want to map it onto an annulus of a greater radius this is 1 still, and this is r greater than r small. And the conformal map does not exist. The quasi-conformal map exists, and the diffeo exists. Now we want to map this to a punctured disk. Then the conformal map does not exist. The quasi-conformal map does not exist, and the diffeo exists. So these are the illustrations for the quasi-conformal maps, and I hope that now you feel yourself a little bit more certain with quasi-conformal maps. Okay? Well, so now I continue Kleinian groups. Kleinian groups, I had this abbreviation, and this is a rather short definition. But first of all, I will recall you some particular classes of groups. Fuchsian groups. This is groups of Möbius transformations that are real on the real line. Therefore, they preserve the real line, the upper half plane, the lower half plane, and these transformations are discontinuous in the complement to the real line. That is, the limit points of all orbits are concentrated in the real line. So these are Fuchsian groups. There are quasi-Fuchsian groups. They are discontinuous in a union of two topological disks, similar to Fuchsian group, but now the complement to the union of these disks is not a real line, which is a circle, accurate geometric circle on the Riemann sphere, but rather the set of limit points is a topological circle. And the complement to this topological circle is the union of two topological disks. And this union is the discontinuity region. This group is called quasi-Fuchsian, and its factors, that is, factor spaces of the discontinuity region over the action of the group, are homeomorphic Riemann surfaces, but in general, they are not symmetric, as in the case of the Fuchsian group. One is of one conformal type, another one is of another conformal type. And we can realize any such pair as a factor of some quasi-Fuchsian group. This is what I explained last time. And now Kleinian groups. It is a group of Möbius transformations with a limit set lambda, discontinuity set lambda is closed, discontinuity set omega equal to C minus lambda, and it is non-empty this is the only requirement that distinguishes Kleinian groups from all the groups of Möbius transformations. And the factor space you identify all the points of any orbit and consider it as one point of the factor space. The factor space is called the factor of G. And in a few minutes, I will pass to a fundamental theorem by Alfors. This fundamental theorem says that though in this setting the factor looks quite mysterious, yet if the Kleinian group is finitely generated, then this factor is a finite union of Riemann surfaces of compact type. This means that any Riemann surface is a finite genus, that is a compact Riemann surface with a finite number of punctures. So this is the statement of the Alfors theorem. I will write it down later on the blackboard. But now I want to go back to the previous lecture and say that, in fact, the previous lecture contained a technique of so-called quasi-conformal deformations. So the connected components of the factor are just called components, and the technique of a quasi-conformal deformations is the following. You take a group, you take its factor, you suppose that the sum of the components is a Riemann surface of a finite type, then you can construct a new group. A new group is the following. You take a Riemann surface diffeomorphic to the previous one, an arbitrary one, and the technique of the quasi-conformal deformations allows you to construct a group whose factor will be the same as in the previous case, except for the distinguished Riemann surface. And this distinguished Riemann surface will be replaced by another one with its own complex structure. So now I recalled this to you by words. I will repeat. I will write down what I have said in words. Suppose that G is a Kleinian group and its factor is S0 plus S1 plus and so on. And let S star be diffeomorphic, another Riemann surface diffeomorphic to S0. I will go to that blackboard that I did not yet use. Here on this blackboard, my section 4 is continued. The quasi-conformal deformation techniques allows us to say that exists a group G1 isomorphic to J with the discontinuity set and the limit set changed, and with factor omega 1 over G1 equal to, I have here S0 replaced by S star, and all the other components are the same. And I recall you very briefly how it was done. The steps. We have a projection pi of the domain omega to the factor. So I am interested in the inverse image of S0 for this projection. Those components that under factorization come to S0. So this is the domain to be considered. Step 1. Bring the complex structure on S0 by a pullback of the map of S0 to S star as a quasi-complex structure on S0. Step 2. Take a correspondent Beltrami coefficient on this domain So this Beltrami coefficient is defined only on some sophisticated subdomain of the Riemann sphere. We extend it by 0 to the whole Riemann sphere. to the whole Riemann sphere. Then solve the corresponding Beltrami equation on the whole sphere. Take the solution it will be holomorphic outside the domain where the Beltrami coefficient is non-zero, outside this domain. Take the solution H, which is the map of the Riemann sphere onto itself, and take G1 to be equal H to the negative 1 of G of H. And this will be the desired group. Its factor will be, first factor will be biholomorphically equivalent to S star, and all the others will be unchanged. So I understand quite well that I do not tell you all the details. I just recall you what was told in the previous lecture, and even if you forgot it, just take it like a program to act and believe that it will be successful. Okay? So now I prove, in quotation marks, the Alfors finiteness theorem. And this is one of the central pieces of the lecture today. So this is Alfors finiteness theorem, a celebrated theorem of 1964. It claims that a finitely generated Kleinian group has a factor of finite type. For sure, I will not give you the complete proof of this theorem, but I give you a proof of a particular case. So the theorem claims that the existence of infinite number of components of the factor is impossible. I will explain you a particular case why the existence of one component of the factor, but with a very high genus, is impossible. And there will be a proof based on the quasi-conformal deformations, and I will try to communicate you the main idea of this proof. And the same idea applied to the general case proves the theorem, except for one particular case, which I will not even discuss today. So the proof in the particular case, something is impossible. So I give you the idea of the proof. Let n be the number of generators of our Kleinian groups. Any Möbius transformation is characterized by three complex numbers. So the dimension of the set of groups G with n generators considered up to conjugacy. You may take, you do not have a distinguished coordinate system on the Riemann sphere. So you take a group of Möbius transformation written in one chart, but if you choose another chart, which is a Möbius image of the original one, then you will get another formulas for the generators of practically the same group. So I consider a group modulo conjugacy G with n generators modulo conjugacy by a Möbius transformation. And the dimension is the following, the complex dimension. 3n for the generators minus 3 for the conjugacy. Let a component of the group G be a Riemann surface of genus G with no punctures. You can in the same way consider the case of punctures, but I do not want to do that. Definitely, the conjugacy does not change the factor at all. The factor space of two conjugated groups is the same. So, if the factor spaces are different, then the groups are not conjugated. They are different elements of this set. So let G be greater than n. And we will bring this assumption to a contradiction. Take any Riemann surface let a component S0 I write for brevity a component of G. Probably it is better to say of the factor of G. Let me add it. So let the factor of G be like this. Like this, S0 plus S1 and so on. And the genus of S0 is G. Take any Riemann surface S star, which is diffeomorphic to S0, which is a Riemann surface of the dimension of the genus G. Do you remember, we discussed this in the previous lecture, what the complex dimension of Tg is? G minus 3. And it is greater than 3n minus 3 because G is greater than n. Let the factor of G be as written there. Let G1 be a quasi-conformal deformation of G as explained in the previous section. With the factor omega 1 over G1 equals S star plus the same. The dimension of the set of the groups G1 thus obtained will be equal to the dimension of the factors of the components of the factor S star will be equal to 3G minus 3. It is greater than 3n minus 3. So we got a set of Kleinian groups which are isomorphic to G, that is, they have n generators, and the dimension of this set is greater than the dimension of the Kleinian groups with n generators. This is a contradiction. So, if you suppose that the Alford's finiteness theorem is wrong, then by the techniques of the quasi-conformal deformations, you may prove that the dimension of the set of Kleinian groups with n generators is greater than it is in fact, and thus get a contradiction. So this is an idea of the proof of the great Alford's finiteness theorem. Okay? I explained you this theorem, and you may consider that this is one of the main goals of the lecture today. I described you quasi-conformal maps. I recalled you the techniques of quasi-conformal deformations, and I explained you, I gave you a sketch of the proof of the Alford's finiteness theorem. So you may consider that the first goal of my lecture today is already achieved. And the second goal is proclaimed there at the beginning. And let me go forth to this goal for sure in a very sketchy manner. I have spoken about three kinds of groups: Fuchsian groups, quasi-Fuchsian groups, and general Kleinian groups. In between, by the two last classes, there is a class of B groups, and I will now describe it for you. B groups and their factors. A B group is a Kleinian group with a specific property of the discontinuity set. The discontinuity set contains a domain omega 0 Omega 0 is a topological disk invariant under the G action. So for any element of G, G of omega 0 equals to omega 0. Fuchsian and quasi-Fuchsian groups are examples of B groups. B groups are named in honor of Birth, who discovered them. And if the B group is not quasi-Fuchsian, then the other part of the discontinuity region may be organized in a very complex way. It may contain a countable number of components that are permuted by the action of the group G. I will say nothing about that. I will now describe a theorem by Musket that gives a complete description of the factors of B groups. So, factor of the B group, factor of G, omega G over G. First of all, there will be an obvious component as G preserves the set omega 0, then the factor space is a Riemann surface. And it is, by the Alfors theorem, a Riemann surface of a finite type. Say genus G and n punctures. Plus, according to the Alfors finiteness theorem, there should be a finite number of Riemann surfaces of finite type. Up to now, they are completely mysterious. And what I will do now is to describe them. I give you the description of all this according to Musket, who worked closely together with Beers, given on 1970. You take the surface S0. This is S0. You take a set of loops which are simple circles, not self-intersecting, not pairwise intersecting, and not freely homotopy to each other. For instance, like this, like this, like this. Then you cut S0 along these loops. I first plotted this cut, then this cut. Every cut produces two holes. There is one hole, so when I cut along this loop, I get two handles. And every handle is also cut along the yellow loop. After that, inside every hole, you glue in a punctured disk. So you have a hole, and this is only a part of the picture. And you glue in a punctured disk. Then you get something like this. A punctured disk is glued in, and this is the puncture. So you get, in this particular example, two Riemann surfaces. They are now Riemann surfaces of a finite type with a and there will be another one. and we call this S1 0, S2 0. And this is S0. So I will say in words what the factor of the group may be, but first of all, I want to be sure that you followed my construction. Did you? I take the curves on S0, I cut S0 along these curves, I get pieces of two-dimensional surfaces, I glue the holes by the punctured disks, and I get the surfaces of the finite type, not Riemann surfaces because there is no complex structure on them. Okay? And though these two topological surfaces by a complex structure, they become Riemann surfaces. This will be S2, and S1 plus the complex structure, I do not write this, becomes S1. So the factor of G, this is the Masked theorem, is either S0 plus S1 plus S2, or S0 plus one of them, or S0 only. This is the description of the B group. And if you included all the possible factors, then G is non-degenerate, or sometimes it is called completely non-degenerate. So this is another piece of information, factors of the B group. Now let us go to the simultaneous uniformization.
So it is the only two S1, S3 are never compacts.
Yes, they have a puncture. But this is a good Riemann surface, a compact Riemann surface with a finite number of punctures. This is a Riemann surface of the finite type. Okay? So now I take the family of the Riemann surfaces with only one critical fiber, and this is a Morse critical point. That is, by the Morse lemma, you have a neighborhood where the foliation is biholomorphic to this simple foliation. Two intersecting complex line is the case of C equals 0, and complex cylinders otherwise. And when uniformizing of this family, we take phi b So this is the zero parameter value. This is the non-zero parameter value. You take S0 equivalent to phi b, b non-equal 0. And you take a group GB with the factor phi b, and another factor is non-depending on B. It is a Riemann surface symmetric to phi 0. Notice that in the neighborhood of the Morse critical point, you have this vanishing cycle. And when you cut phi b along this vanishing cycle, you get two holes. Then you include two punctured disks in every hole. And this is exactly the construction of another component of the factor in the B group. So you take the family of B groups with these factors. They may be realized according to the Masket theorem. And it appears, it is a non-trivial result, but it may be proved, that the set of the groups GB is a set of B groups. The topology of their factors is the same for B non-equal to 0, but for B equal to 0, you have the factor phi 0 bar. So you get a group conjugate to a Fuchsian one, and it may be proved that all this family of groups depend continuously on B, and the domains omega B for GB, omega 0 B, this simply connected domain invariant for the group GB, is just conformally equivalent to the universal cover over phi B. So this is just an illustration. I do not pretend that I gave you a proof, but I think that I give you an idea of the world that is involved in the uniformization of algebraic curves with variable topology. So this is what I wanted to tell you. And once again, I recall that in the next lecture, I completely change the subject and switch to real dynamical systems and to bifurcation theory. And again, I will present you the bifurcation theory from the very first steps, just in the survey manner, up to the up to the new results and unsolved problems. So this is the goal of my next lectures. Thank you. I am ready to answer questions. Well, the talks will begin soon. Yes, please.
When you make this surface with complex structure, is this complex structure, when you use S1 or S2 plus complex structure, is this complex structure unique in some sense? It is always possible?
No. Whatever complex structure you will endo, you may find a group with the factors with exactly this complex structure.
Okay. Thank you.
Yes?
We were wondering whether you could elaborate on the meaning of a Riemann surface being of finite type.
This is that its closure is a compact Riemann surface of finite genus, and the difference with the closure is a finite set of punctured points.
All right. Thank you.
Gn, as I wrote several times. Yes?
Can you repeat why you, when you were talking about the Morse critical point, why you wrote that equation? CW equals C?
This is the Morse lemma. It claims that an analytic function in a neighborhood of a non-degenerate critical point, that is, the second differential is a non-degenerate quadratic form, may be in some analytic coordinates written as the function constant plus zw. And the level curves are by holomorphic equivalent to zw equals c in the neighborhood of the Morse critical point. Yes?
Is this Alfonso's proof of the finiteness theorem?
It is his main idea, yes. Well, thank you.